Dr. Tom, are you still with us?
Yeah.
Okay, then I will give a little bit introduction, then we will play the prerecorded video, and the Q&A session will be carried out by you and Dr. Ganesh, if I understand correctly. Okay, then as you may know that if you have the open source culture, still you have to have an open source design. Without open source design, the open source stuff is not guaranteed to be open. So we're very grateful to have Dr. Shivantan and Ganesh to share their work. So here we go.
Hello everyone, today is my pleasure to talk about the OpenFPGA project as well as this open source FPGA IPs. I'm Shivantan. So nowadays you may see that FPGA is everywhere. So FPGA has unique advantages in modern computing systems. That's why you see it very popular in the wired and wireless communications, where FPGAs serve mainly as interfaces between different protocols, communication protocols, such as PCIe, SPI, and I2C. Also, in recent 10 years, you see FPGAs has become a dominant component in modern data center systems, where FPGAs work as co-processors, or we call accelerators, sitting aside to CPUs. Their main job in such systems is to do high-performance computing, such as signal processing, AI inference engine, and image processing. Also, FPGAs are very popular in defense industry, where FPGA can be regarded as a secure media providing logic obfuscation to prevent attackers to know what the exact logic of a SoC. Let me give a brief introduction by showing this video about OpenFPGA.
Market is critical for any IC company, especially FPGA vendors. In line with our customers' needs, the company that can deliver products faster earns most of the market share. However, current design methodologies for FPGAs require year-long developments and hundreds of engineering months when moving to a new technology node or bringing to market a new architecture, longer than what is needed for even a complex SoC. As an FPGA vendor, QuickLogic is actively searching for agile methodologies and automation technologies to compress our development times.
My name is Pierre-Emmanuel Guyardon. I am an associate professor at the University of Utah, and I am leading the development of OpenFPGA. OpenFPGA is an open source framework that enables the agile prototyping for customizable FPGAs. Using OpenFPGA, hardware development is way simpler than before. By exploiting cutting-edge design automation techniques, OpenFPGA can reduce the development cycle of a new FPGA from a year long to less than 24 hours. OpenFPGA provides out-of-the-box open source design tools for your FPGAs. Thanks to the open source community, your FPGA tools can continuously benefit from the latest advancement in FPGA technology. OpenFPGA allows users to customize their own FPGA in minutes by leveraging a rich set of templates. Constantly growing, OpenFPGA provides an architecture library which includes more than 20 state-of-the-art FPGA architectures, covering a wide range of application domains. Do not feel lost if your application is very special. OpenFPGA's architecture description language allows you to craft your own FPGA fabric. We provide tutorials and a detailed manual to guide you through the design of your own FPGA architectures from scratch. Using OpenFPGA's reference methodology, physical design becomes an easy job. Fabric Verilog netlists and timing constraints are automatically generated from your architecture description files. We support most of the commercial physical design tools on the market. By simply pushing buttons, your production-ready layout can be finished within 24 hours. We support a wide range of commercial and open source verification tools. This allows you to perform functional verification, formal verification, and timing sign-off in a quick and easy way, effectively making sign-off a one-man job. Tooling is a big software endeavor for an FPGA vendor. OpenFPGA provides end-to-end EDA tool support for any FPGA fabrics that can be described by our architectural description language. OpenFPGA automates the design of FPGA fabrics through a very agile development approach. It enables domain-specific architectures with built-in security features relevant to most stringent needs from civil and defense applications.
Thanks to OpenFPGA, we can convert customers' needs to prototypes in an agile way. We are confident to extend our product portfolio and extend our market. And moreover, this enables us to make decisions faster, which inherently speeds up innovation and reduces risk.
All the source code and documentation for OpenFPGA are available on GitHub. Please feel free to fork and start to build your own FPGA today.
So after displaying this video, you may give a basic idea about how OpenFPGA looks like and why we need OpenFPGA. Let me summarize what you get. So OpenFPGA is currently a leading open source FPGA IP generator. It supports very highly customizable FPGA architecture designs. We provide most complete open source EDA support for the FPGA IPs that are going to be generated. We also enable 24-hour development cycle for FPGA IP generation, which is currently the leading tools you can have in the field. Due to these features, we have received Best Contribution Award in the WorldSat 2020 workshop. Also, I would like to mention that the Open Source FPGA Foundation was launched in March 2021. The idea of this foundation is to democratize FPGA technology by providing an open, user-focused, and a collaborative environment. And we are very fortunate that OpenFPGA is now a project under the hood of the OS FPGA Foundation. For more information, you can visit our GitHub as well as the foundation website, which is attached in this slide. So let me give a deep dive in the OpenFPGA framework. So first of all, OpenFPGA is a fully modularized codebase where we integrate various tools from collaborators, mainly open source. The idea of OpenFPGA is to sit on top of the well-established and popular FPGA research tool called VPR. So VPR was invented 20 years ago as an FPGA architecture exploration tool. It has been very heavily used in FPGA research world. If you search or Google the most popular FPGA conferences, you can see VPR tools are used in most every papers you see. So that's why, given the fact that VPR is extremely popular in FPGA world, and it offers very flexible architecture description language, OpenFPGA reuses the VPR architecture description language and being compatible with the architecture description file, so that any VPR users will take least effort when immigrate from VPR project to OpenFPGA project. It means once you have a project or once you have an FPGA architecture evaluated under VPR, you can directly use OpenFPGA to prototype it. This makes your architecture innovation much easier than before. So OpenFPGA is a unified codebase, a unified framework which can do multiple objectives. The first objective is the chip design flow, as highlighted in this figure. The idea is you have done the architecture exploration using VPR. You have established your architecture description file. And then you can use OpenFPGA to prototype this FPGA architecture by converting or compiling your architecture description to a physically fabricable layout. You can send this layout to Foundry and fabricate your FPGA chip. Another design flow is the end user's design flow. This flow is extremely useful when you have your chip fabricated by the foundry. So it means when you get a chip, this is the compiler you can use to compile your HDL designs, such as Verilog design, into bitstream that can be downloaded to the FPGA and configure the FPGA to the functionality you want. And last but not least, OpenFPGA complies with standard file formats and third-party tools, so that it's a very modern software platform with strong compatibility. Talking about the compatibility, OpenFPGA has shown we are able to support many third-party tools in our design flows. In the gray boxes here, as you see in the figure on the left, they are the third-party tools that has been supported by OpenFPGA or integrated to OpenFPGA already. There's some highlights I want to mention. First, the backend tools. We support most of the commercial state-of-art backend tools, such as Synopsys IC Compiler 2, as well as the Cadence Innovus. For STA, we do support Synopsys Primetime and Cadence Tempest as well. For HDL Simulator, we support not only Synopsys VCS, mental models in Cadence, as well as the open source Icarus iVerilog. You can also use formality tools to verify the FPGA fabric before you send it out for fabrication. And OpenFPGA has been tested on many PDKs, including the Academia ASAP 7nm, as well as Global Foundries, TSMC. Also include the open source Skywater 130nm PDK. So OpenFPGA's feature includes that we strive for supporting fully customizable FPGA architectures for our users. It means we allow chip designers to customize any circuit elements at any location of the FPGA fabric. For example, in this figure, on the left side, we show the complete FPGA fabric, as you may see in the commercial vendors. We allow people to customize a single multiplexer inside a logic element block with a dedicated or special multiplexing structure. In this example, as you see, it's a one-level multiplexer. However, chip designers may prefer different type of multiplexers by trading off area, delay, and power. In this example, we show that people can also customize the routine multiplexers in a different location. That's the connection block, saying that I don't want a one level here, but I do want a two-level multiplexer here for better performance. Same philosophy can be applied to the registers or sequential elements in the FPGA architecture. For example, in the data pass flip-flop, you definitely want to use the high-speed flip-flop to guarantee highest performance of FPGA. However, in the configuration memory, people may prefer some low-power flip-flops to achieve low power to minimize the configuration power of the FPGA. And also, you may know that FPGA may have different ways to configure that. OpenFPGA offers language syntax to allow people to customize the configuring protocol circuitry as well. So that's the overall features of the OpenFPGA. Let me have some showcase to tell you how capable OpenFPGA is through a practical open source eFPGA project. In this slide, I'm going to focus on the Skywater Open-source eFPGA, whose short name is SOFA project. The SOFA project includes a series of embedded FPGA IPs, including the base design SOFA HD, arithmetic enhanced design QL SOFA HD, as well as a performance optimized design called SOFA CHD. All these eFPGA IPs were implemented in the open source Skywater 130nm high-density standard cells, being compatible with the Caravel SoC framework. As I said, these eFPGAs are open source from top to the bottom, means from the Skywater PDK to the final layout. You can find everything on our GitHub as well as the datasheets online. So for these three versions of eFPGA IPs, they offer different levels in trading off area, performance, and device capacity. Here is the table summarizing the difference between these three eFPGA IPs. As you can see, in general, they have 1.2K 4-input LUTs in the device. I would like to highlight that QL SOFA HD and SOFA CHD do have the support on soft adders, which can implement arithmetic functions such as adders more efficiently than the base design. In the later two eFPGA IPs, we also boost the routability by adding another 30% more routing tracks to the architecture. More interestingly, in the SOFA CHD version, we developed a few high-performance cells which can boost the performance by 2 times, and details you may see in later slides in this presentation. So what does SOFA offer? So our big motivation when developing this SOFA project is to benchmark the OpenFPGA framework, to validate its effectiveness when automating the development cycle for eFPGA IPs. It's also a good showcase for OpenFPGA, saying that we are very compatible to different PDKs, especially the open source Skywater PDK. We do want to also provide open source FPGA fabrics, architectures, as well as OpenFPGA EDA tools for academia researchers and industry partners. Is a very good example how you should use OpenFPGA to develop your FPGA IPs. So the deliverables of the SOFA project includes fabrication-ready GDS2 layouts, as well as the post-layout Verilog netlists with which you can run verification to validate the correctness of your FPGA before sending out the GDS2 layout for fabrication. We also provide end-user design tools which can convert or synthesize your Verilog design into downloadable bitstream. We also offer the data sheets for all the eFPGA IPs we have created, allow you to optimize your Verilog design to the most fitting the architecture features available in SOFA FPGAs. So all the SOFA FPGA IPs are created by the OpenFPGA Framework through an automated design flow. This results in a very short iteration cycles to validate the physical design of an eFPGA IP. Starting from the PDK adoption to the final layout, the end-to-end iteration is less than 24 hours. Remember, in FPGA industry, the typical iteration will be maybe a few months because the extremely high manpower or human resource involved to deliver a validated physical design of an FPGA. Due to this significant reduction in manpower requirement as well as the time requirement, it takes only 3 engineers 3 months to finalize the 3 SOFA FPGA IPs. It includes 1 architect like me and a physical designer like Ganesh, who is going to present later in this presentation, as well as a sign-off engineer. So compared to hundreds of engineers involved in commercial FPGA product development, we have significantly reduced the manpower requirements. So all the eFPGA IPs follow a tile-based FPGA architectures, as you see in modern FPGA products. I show a brief organization in the figure at the bottom about eFPGA IP. They all consist of a 12 by 12 array of logic tiles. Surrounding the logic tiles, there are 36 low-power I/O tiles, as well as 12 high-density I/O tiles. All the eFPGA IPs are modeled in open-source architecture description files. They are compatible with the VPR's architecture description language, and it means in the figure I show on the right side, people can easily run VPR to get, or OpenFPGA to get utilization rate, timing passes, as well as power estimation, and also bitstream for the designs. For so far FPGA IPs, it means the embedded FPGA technical details are fully open to developers. This is something you can never imagine in the commercial world, that their FPGA vendors or creators can be so transparent to developers. So all the eFPGA IPs are integrated to the Caravel SoC. It means, you see that in this organization, the eFPGA IPs can interface a RISC-V processor, EDAS Pico RV32 here. The eFPGA do have 36 external IOs for users, through which you can operate the eFPGA as a standalone FPGA, as usual as you see in FPGA products. Also, the eFPGAs have 108 internal IOs to interface the RISC-V processor. You can interface the RISC-V processor through 2 ways. One is the wishbone bus. You can enable the FPGA to operate as an accelerator sitting aside to the RISC-V processor, or you can use the logic analyzer to read back signals or read in signals to the FPGA, so that you can really run in a debugging mode for the eFPGA. So that's the general architecture features for the eFPGA. Now I will shift the stage to Ganesh, talking about the end user flow about the OpenFPGA in the SOFA eFPGA IPs.
Hello everyone. Continuing the discussion on OpenFPGA, we will discuss how to use end user flow to generate configuration bitstream. The end user flow starts with specifying task configuration file, which contains user's design and few parameters related to OpenFPGA. OpenFPGA engine reads this task configuration file, performs synthesis, pack, place and route operation to generate the bitstream. There are several results generated during this flow which can be analyzed later to better understand the implementation. The results like resource utilization, max operating frequency, timing paths are readily available at the end of the flow. For example, the 8-bit counter benchmark running on 3 different SOFA variants results in 32 MHz and 55 MHz max operating frequency. Let's look at the demo of how to run a sample user flow using OpenFPGA for SOFA design. I have cloned the SOFA repository and you can see 3 different projects in this directory: SOFA HD, SOFA CHD and QL SOFA HD. For this demo, we are going to implement a 8-bit counter design in QL SOFA HD project. To find a task configuration file, follow PNR directory, task directory and configuration directory. The tasksimulation.conf lists all the variables required for OpenFPGA user flow. In this file, you can see all the variables related to OpenFPGA are already set up. In the benchmark section, you can see a Verilog file used during this flow. To run this task, go to PNR directory and make run OpenFPGA. During the OpenFPGA run, it's going to create a latest directory inside your task directory, which will contain all the results as well as bitstream file. To look at the results, open latest directory and open the CSV file. The CSV file contains how many IO blocks, packing time, placement time, all other information extracted from this design. To find a bitstream file, follow the hierarchy to get the .bit file in the same directory. Thank you.
As such, you have seen a very good live demo from Ganesh about how to generate a bitstream from your Verilog design for the SOFA FPGAs. Here are some future works as a next step for the SOFA project. First of all, we want to develop fully open source FPGAs from architecture to GDS. It means we want to use the open source framework, open road, to produce the same quality of FPGA IPs as you see in previous slides. Second, we want to upgrade our SOFA FPGA IPs to be more heterogeneous with embedded IPs. As you see in the figure on the right, we want to integrate block RAMs empowered by the open source OpenRAM project, as well as DSP blocks can be developed through the Open Road project. And here are some concluding remarks. So OpenFPGA do enables Angel hardware development for FPGAs. We support fully customizable FPGA architectures, and we provide adaptive and auto-tuned open source tooling. We released 3 open source eFPGA IPs, which are the Skywater embedded eFPGA IPs. Everything is available on the GitHub as well as the data sheets on these eFPGA IPs. And we may also pay attention that there are some in parallel projects that use OpenFPGA to generate FPGA fabrics using the OpenLAM project. And that's the end of the presentation. Thank you very much.
Hello. Welcome back, and we are doing the Q&A on Slido. And here's the questions. The first one: does SOFA support hard IP like DSP slice?
Yeah, I think you already see our slide, the last 2 slides about a SOFA Plus version, where we do have hard IP like DSP slices. And actually, the SOFA Plus version is under taping out in the eFpgAs MPW2 project program. You can search the project on the eFpgAs website.
Oh, will do. I know your project from eFpgAs, and that's a personal your great work on this. And the second one: does current open source FPGA flow on chip logic analyzer IP like integrated and logic analyzer? Well, that's a kind of confusing question.
Yeah, no problem, no problem. I get the idea here. So currently, we're still investigating the possibility to integrate some logic analyzer IP, because we have not done so before. Because the reason behind is that we are focusing on a fully open source FPGA flow. It's not like, I would like to clarify, it's not like Simbi flow that you are applying an EDA tool on existing FPGA product. OpenFPGA is a tool to allow you to tape out your own FPGA. Imagine you can create an FPGA like Xilinx. You don't need to buy it, but you use OpenFPGA to fabricate it yourself. So that's why we're building a vibrant community these days, and we're looking forward to more contributions such as logic analyzer, IPs to be integrated in OpenFPGA. I mean, I'm the maintainer of the OpenFPGA project. I would love to see such contribution. And from my point of view, my understanding on OpenFPGA is fully doable.
I see. Okay, next question. How should software developer get into OpenFPGA development? Well, get it, learn from the course. I don't know.
Yeah. I get the idea here. So, Ganesh, do you have anything to say before I start?
Oh, so we have a very good documentation for the entire OpenFPGA project. So if you start reading from the documentation, OpenFPGA as well as VPR documentation, I guess you will have a very good start, and software engineers can also start with FPGA development.
Yeah, so Ganesh has mentioned a very good point. As I would say that we are enriching our tutorials on OpenFPGA documentation website, and you can find more and more tutorials talking about how to use OpenFPGA, assuming you have no background, assuming you are pure software developer with this knowledge on hardware development.
I see.
And yeah, that's something we're doing. Also, if you use more OpenFPGA, you will realize we are making a hardware project more and more like a software project. We're introducing a lot of CI features that you see in the modern software project. We enable that in OpenFPGA so that you can develop an FPGA chip using the modern software techniques.
I see. And the next question, is there publicly available type of OpenFPGA chip, either FPGA or eFPGA? I see there's a project called Core 5 and so I know that's from QuickLogic and the eFPGA fabrics, I believe, but is it related to OpenFPGA?
I have very limited knowledge on the Core V MCU, but I would pay attention to that later. I think it will be a very interesting project. The question here, I think, has been already partially answered in our video, where we already demonstrate 3 eFPGA IPs, and they're open source on GitHub. Let you know how to use OpenFPGA. And we do have also some 12 nanometer FPGA chip taped out using OpenFPGA, and we are currently testing it, and hopefully we'll release some information next month. And also you'll see we are going to release more and more open source FPGA IPs by following this trend this year and next.
I see. What FPGA chips are supported by? It is a framework for you to do, so I think this problem is I will jump over. Sorry.
No problem.
Any plan to support dynamic reprogramming?
Yeah, so we do have many configuring protocols for the FPGA supported, because as I said, we're talking about making your own FPGA chip rather than using an existing FPGA chip. So we do have many various configuring protocols for the FPGA, which already covered some part of the dynamic reprogramming features. So please visit our website and search config protocol in OpenFPGA documentation.
I see. We can have the one last question. Is there comparison between the bitstream from OpenFPGA and commercial FPGA tool, like number of gate compile time, and etc.?
Yes, I think it's a currently ongoing project on our side. We're actively testing that, but it's not easy to benchmark all the corners, because OpenFPGA is a very generic tool. We're not targeting only one type of several product line of commercial FPGAs. We unlocked many possibilities for users. You can imagine what the FPGA you want. I mean, for example, in the commercial world, you want an FPGA with a lot of DSPs or VRAMs, which currently commercial vendors cannot offer you, but OpenFPGA can do it for you.
Okay.
We can make it true in like 24 hours for you.
Okay. I just skipped this question, but I believe he deserved to be noticed or answered. I'm not quite sure what he's trying to asking. Maybe do you want to try to understand or you're okay?
Yeah, I mean, if you say what FPGA chips are supported, it's mainly the FPGA we're taping out here. It's a very not special. I mean, it's still very generic FPGA architecture, which is very well optimized or tuned to the eFpgAs Caravel framework. So if you say what is supported, try the SOFA project and you will find it out.
Okay. Well, we have 3 minutes. We're actually, I'm sorry. We're over time, so I'm trying. I will pull off everyone from the Shunyar now, and thanks again to Dr. Xifan Tang and Ganesh for their wonderful work on open sourcing literally everything on designing an FPGA. And thank you. Bye bye.
Thank you.
Thank you.